Okay, we got our review here for Q-2-1. It looks like we're going to be doing the energy problem first. A couple things. We have a mass of 1415. Kind of put in our forces here. We have FMG, which is down. We're pushing it at an angle. That's going to result in both a X part of the push and then also a Y part of the push. Our components here. It's a 25-degree angle, so the X will be more than the Y will be. Okay, we also have Fn. The blue plus the black will give me my overall arrow. Make sure it's bigger. And then we have one more thing that's helping us stop it, and that's friction, FFK. So really we have 4 forces, but you'll notice that I have a total of 6 arrows here. So don't be confused by that. The red and the blue are just the X and Y part of the push. And then here we are trying to stop the object. We're going to do this for 16 meters. Just kind of push back. What we really need to do is just figure out the net force in the X direction. That's the goal. There's a number of things we have to do to get there. First, find the weight. So we're going to say 1415 times 9.8. So we get 13,867. Now we can kind of break down this push. It says right here it's 400 directed at 25. Okay, we're not going to use 400 for anything. The first thing we want to do is find the blue arrow so we can find the force of normal. If you look at this arrow, we can resolve it, which means if we have 400 at 25 degrees, some of that will be in the Y. That much of it is in the Y. And then that much of it is in the X. So the angle is touching here, the red. That would be cosine, that will be sine. So we're going to say 400 times the sine of 25 degrees. That's going to tell me my blue arrow, 169. 400 times the cosine of 25 gives me my X arrow, which is 362 and a half. So these two things together will be used at different times. First thing I want to do is use 169. So if this is 169 right there, we can then add that to our weight. So remember, it was 1415 times 9.8 plus our previous answer. So we get this big number, plus 169. 1436. So that's the force of normal. 1436. Now we're ready to find the friction. So to find the friction, we use another equation. We're going to say FFK is equal to mu k times the force of normal. The force of normal is 1436. Mu k right there, 0.09, and we can find out what friction is. So take your force of normal number, and multiply it by 0.09, and we end up with 1,263. So that's this arrow right here. Now we're going to take this and add it to that, and that's going to be the net force in the X direction. So I know that's a lot of work to get us to the point where we know what the net force is. So really we really do a lot of work to come up with net force in the X, like almost 4 minutes worth of work to get there. So let's go ahead and we'll add it together. We've got 362 and a half. That was the red arrow or the push, plus the friction, 1263.24. So the net force is 1,625.74 newtons. That's a big part of what we got going on here. That's the first step, is coming up with that number of net force. Once you get that, you know, in my opinion, really a lot of the hard work is already done. Now we can kind of do this the old way and the new way. Let's do the old way first. That should be more familiar to you. Just fold the paper here. So first thing we're going to do is use Newton's second law to come up with the acceleration. So we put in our net force, and we put in the mass, and we solve for A. So I already have this in my calculator. I just divide by the mass. The acceleration is 1.15. Now it's going to be negative. The reason for that is because as we push this object and walk backwards, we would set up our square root to the right. So as we move across this in 16 meters distance, you're progressively slowing down. The motion diagram would look something like this. Of course, go a lot further. Try this again. Yeah, that's looking better. So that would be our motion diagram. So now we're going to plug that acceleration into magic physics formula number 4. And we're going to try to solve for V naught. So if we're successful, it will stop. We got our V naught right here. We've got 2 times the acceleration, negative 1.15. And then we've got D and D naught. Remember, we started at 0, and D would be 16. So when you simplify this, you're going to end up with a negative over here, but when you move it over to the other side, it's going to become positive. So 2 times that negative acceleration times 16 gives me this number. But remember, we're going to make that number positive by moving it over to the other side and then square rooting it. And you get 6.06 for V naught. So that's the first 2 answers. A, negative 1.15, and V naught would be 6.06. Okay, we're going to get 6.06 again, but we're going to do it a different way now. So when we do it the second time, we're going to focus more on this work idea. So the idea being that if we have a net force, we can also then get a net work. Work is equal to force times distance. So if we take that net force, which was 1,625 3/4, and we multiply it by 16, we'll get a work. Remember, this is scalar quantity, so we don't have any signs that we really have to worry about throughout this entire process. 2612 joules, or Newton meters, whatever you want to say. Once you get your number of joules, that would be our net work, 2612. Remember that work is equal to a change in energy. Here my energy would be energy of motion, or kinetic energy. So another way to say that would be 26012 is equal to 1/2 mv final squared minus 1/2 mv initial squared. We're going to stop this, so this will be 0, and we can kind of get rid of all that. And then remember, it's a scalar, so signs don't matter. So we're left with 26012 equals 1/2 mv squared. So 26.012 is equal to 1/2 of 1415 equals V naught squared. So you're going to see real quick, take that net work divided by 0.5 times 1415. Whoops. And then we're going to square root that, and you get the same thing. So that's nice that you can check yourself that way. Really, you're just doing the same thing. You're just putting that distance in at different times. You can put the distance in before, put the distance in afterwards. You're still going to get the same answer. Physics works, which is good. So that's 9 minutes. I know that was a while, but I think it's time well spent.